If I could issue a warning to help you avoid problems on the exam. I'm an old man, I've been doing this a long time. And what I see is that over and over again, people try to find the frequencies of different harmonics using these formulas. That are in the formula dump. Now, they weren't in my original version of this chapter 15. They were added because a lot of people like to use them. My experience, again, as an old man that's seen this go down a lot, is that almost everyone that uses those formulas gets the wrong answer. And that's because they use the wrong formula, or they use the wrong value for n, and it's a mess. And so I would encourage you to just forget about those. Just forget about those. And use those two formulas that are over on the right. Okay? You can always use the wave equation. And that's going to work for every harmonic. I don't have to worry about the value of n. Okay? And it's also going to work whether you've got the n's the same or the n's different. So you don't have to worry about which equation do you use. You always use that one. Now, I can't draw a frequency, but I can draw a wavelength. And so, for example, in this problem 10, you're told that the tube is 2 meters long. And I've got the second harmonic going on. Well, if you use those fancy formulas that get you into trouble, you'd have to worry about which one to use, which value of n. But here I just draw the picture and I say, hey, how big is my wavelength? Well, it takes 2 footballs to make a wavelength. I got 2 footballs in this 2 meter long tube. My wavelength must be 2 meters. It's a sound wave, so this is 343 meters per second is equal to the frequency times 2 meters, and I get a frequency of 171.5 hertz, or 343 over 2. Now, if you have a hard time seeing that the wavelength is 2 meters, use that second equation over on the right board. The number of footballs times lambda over 2 is equal to the length of the system. Well, here I've got 2 footballs times lambda over 2 is equal to the length of the pipe is 2 meters. Well, that gives me lambda is equal to 2 meters. I don't even have to know which lambda it is, that it's the second harmonic. I'm still going to get the right answer for the frequency. Okay? Now, that's not the part that got this voted off the island. You're told that while these particles in this tube are sloshing back and forth, remember you in the bathtub scooching back and forth, making the splashing, we take a snapshot. And this point F at the antinode has a big displacement to the right when we took the snapshot. Now, this football representation is a particularly lousy representation. There's nothing that's going this way in this tube. The particles are rushing together to crunch a node or rushing away to desert a node. And each node, well, let's talk about where the node is. The node's not just right there. That's what this football representation would lead you to believe. But in this tube, every particle in this whole layer of gas is at a node. So this point, that particle would not be moving. This particle would not be moving. This particle would not be moving. That particle would not be moving. Likewise, over here, D is not moving. But neither is this point or that point or this point or that point. Now, each of these node areas are being crunched and then deserted, and then crunched and then deserted. That's what this sloshing is, back and forth, back and forth. And that's what causes the sound that comes to our ear. Now, every particle in one football has to be going the same direction. So if F is going to the right when we took the picture, so is E. The only thing the football's good for is telling me how far it's displaced from equilibrium. If the football's narrow, it's not very far. If it's fat, I'm at an antinode and it's big. Now, when one football's going to the right, the neighbor's going to the left, because that means that this node is being deserted. So that means this would be going like that, these guys would be going like that, but also I'd have particles over here that would be going like that. I'd have particles over here that would be going like that. This particle would be going like that and like that. Now, if this node is being deserted when we took the picture, this one's being crunched from both sides. And the closer I am to an antinode, the bigger the displacement. Okay? Now, if I wait half a period, okay, all the arrows would be reversed. Okay? So this one's being crunched when we took the picture, but a half period later it would be deserted. This one's being deserted when we took the picture, a half period later it would be crunched. See if your neighbor understands the sloshing that's going on in that tube.